Thank you so much, Alessandra, for having me here today. So today I would like to talk about how you can do statistics with set of graphs. And as this workshop is about uncertainty, I would like to focus on uncertainty that you might have on the label of your set of graphs. And in particular, I would like to talk about purely unlabeled graphs or abstract unlabeled graphs and graphs that have spatial constraints. So these are the two types of graphs I want to talk about today. So I'll start by introducing what do I mean by set of graphs, then I'll talk about unlabeled graphs in general, unlabeled abstract graph, unlabeled spatial graphs, and then I'll discuss some further developments in the direction of working with a set of spatial graphs. That's pretty much what I would like to do today. So what do I mean by set of graphs? So I really like this definition by Marron about object-oriented data analysis. So when you work with a set of objects, you can work in the so-called first generation or second generation approach. So the first generation approach focuses on the analysis of one single complex datum, for example, one network. You have a set of vertices, a set of edges, for example, you have a transport network. You measure some information on your edges, for example, the number of passengers traveling between stations. And you are interested in understanding properties and studying properties of this single object. For example, clustering the nodes, or predicting an edge, or predicting the activity on an edge. So all this falls into the so-called first generation approach. The second generation approach, which is the approach that we are taking today, is working with a set of objects, for example, a set of graphs. So you have a set of graphs representing, for example, the transport system in different cities. So the questions are different from the one posed in the first generation approach. So you might be interested, for example, in clustering the networks, or predict a new network giving a set of networks, or doing classification. So we're going to work with the set of objects that are graphs. And we're trying to answer questions and do statistical modeling for this population of objects. Now, the first question is, are we working with labeled or unlabeled graphs? So by labeled graphs, we mean that our set of graphs share the exact same set of nodes. So for example, I have Matilde, Lorenzo, and Vittoria. There are three nodes, and I measure the activity between them in time, for example, or in different scenarios. So in this specific case, I know the node label across all my observations. So these are called the node labeled graphs. The second case, these are two extreme cases actually, there are a shade of gray in between, but the extreme other case are purely unlabeled graphs. This means that I don't know which is the correspondence of the nodes across my population. So for example, which nodes corresponds to which other nodes in the other graph. So these type of graphs are called unlabeled graphs, and I have uncertainty about assigning a node label to compare my graphs. Okay? So that's my uncertainty today. Now, what I would like to do today is to discuss two types of unlabeled graphs that can arise in different applications and describe how can you do statistical modeling for a population of these two types of graphs, different types of graphs. So the first is what we call the abstract graphs. I give you this explanatory example. So suppose you have a football match and you have two football teams, maybe France and Croatia, or Barcelona and Inter that played yesterday. So you have the different players and you're studying the number of passages between players. And you built what is called a player passing network. So per each team, you have a player passing network. Now you want to compare different teams. So you don't have the same set of players in the two networks. So you need to find a match, an alignment between the graphs in order to be able to compare the player passing networks. These are called abstract graph in the sense that I don't have additional information about the nodes. So I get rid of the name of the players and I try to compare the graphs. Other type of graphs, which are the second type that I want to discuss today, are again unlabeled, but they have different characteristics. So for example, you might be interested in studying an image, for example, an histopathological image. You extract some structure from that image, For example, this is an image about cardiac fibrotic tissue. So you extract the isolated black part, you do a skeletonization procedure, and you end up with a set of graphs, okay? This set of graphs has a spatial constraint. So I have node positioned in R2, for example, and I want to be able to compare this graph because I have a population of spatial graphs. So again, here, the meaning of these labels, the labels are meaningless because they come out of a preprocessing. So I don't want to consider node 1 to be 1 across my population. This doesn't make any sense. So I want to be able to compare this set of graphs up to a matching or an alignment, getting rid of the node labels that has been created by the preprocessing. Okay? So these are just explanatory examples. This type of graphs arises in many different contexts. But I just wanted to explain the type of graph I would like to work with. So unlabeled graphs in general require a concept of matching or alignment. So this is what we would like to model. And I will discuss these two cases, abstract graph and spatial graph. I'll define a possible geometrical embedding for these objects, and then I'll describe how can you do statistics or data analysis in general for these data sets. For the abstract graph, I'll present a regression model. For the spatial graph, I'll present testing procedure. So this is what I would like to do today. Let's start with abstract graphs. So this is an explanatory example. We've been through this already. So you have to think of a set of graphs that has a different, in this case, actually, they have the same number of nodes, but this framework can code also graphs with different number of nodes. And you have a label that you want to get rid of in order to compare these graphs. So the first question is, how do we want to describe these data objects? So we're going to focus on directed and undirected graphs with finite number of nodes and with Euclidean attributes on nodes and edges. So this is the framework. We're going to describe each graph as an adjacency matrix, which is a standard representation for undirected and directed graph. And we want to encode the uncertainty on the node labeling. And this is done by using a permutation matrix. So I'm going to define a permutation action on the nodes in order to permute the graph and account for this uncertainty on the node label. And this can be encoded in the matrix form by applying the permutation action by conjugation to the adjacency matrix. So I can go from this adjacency matrix to the set of permuted adjacency matrix that I obtain when I permute the nodes, which corresponds to permuting the rows and the columns of the matrix. I can define graph space as a quotient space, x over t, obtained by applying the permutation action that here I'm calling t, by conjugation to the space of adjacency matrix. As I have Euclidean attributes on edges, my adjacency matrix is a point in R n times n. Okay? So this is an intuitive way of working with unlabeled graphs. I can define a metric. The distance between two equivalence classes of graphs is defined in this way. This is a quotient metric that you can define by selecting a distance between two adjacency matrices. I find the optimal alignment by selecting the optimal permutation matrix, and this induces a quotient metric in my graph space. I can also define geodesics, so I can extend the concept of straight lines to this quotient space, and this is done by using they are called generalized geodesics. So I select all my geodesics in the set of adjacency matrix, which are line, plane, and hyperplane, actually. And I can use this pi map, which is a projection function, to project my geodesics onto the quotient space. So pi is just the map from an adjacency matrix to its corresponding equivalence class. So I have this quotient space, and I have equipped it with a metric and a geodesic. So this is just to visualize it, like to have an intuitive idea of what's going on. So I have X, which is what is called the total space, and is the space of adjacency matrices. Now, I have a set of adjacency metrics that collapse into an equivalence class of permuted adjacency metrics by applying the permutation action by conjugation. So all this set collapse into an equivalence class into my quotient space that is called graph space. I can define a distance, as I said, between two equivalence classes by finding the two representatives that are closer to each other according to the metric that I define between adjacency metrics. So I can use different metric in this space to induce a quotient metric on this space. Okay. I can also define a geodesic, so for example, a straight line between two representative of my equivalence classes, and this can be projected as what is called a generalized geodesics between two equivalence classes. Okay, so this is the summary of the concept I introduced before. Do you have any questions so far? No. No, good. We can go on. So, the final goal is to consider a data set of graphs in this graph space, so in this discrete quotient space, and define some sort of statistical methodology to answer some questions that you have about your data. To do so, we need to characterize the geometry of this space in order to see which type of tools I can extend. So this space is not a manifold, which is not a good news because there are a lot of tools that has been defined for data on manifold. So we cannot use any of those. It is actually a discrete quotient space that is sometimes called orbifold, and it is a stratified space. So it is a space that has equivalence classes of different dimensions. Yeah.
So what is underlying metric on matrices?
So I'm using Frobenius norm, but you can use any component-wise metric, and you will induce a quotient metric on the graph space. So this is basically a big summary of what's going on. The positive things is that I have a quotient space that is defined by quotienting space of adjacency metrics, which is a very nice space because it's a Euclidean space. So what I can do is use the geodesic and the metric that has been defined in my quotient space to extend methodology to the quotient space. So we can define methods, as I said, based on metric and geodesics. And today I would like to describe in more detail how you can define a regression model in this context. This type of space, this space has been originally introduced by Jane and Obermeyer. And just to give you some references, and there are other methods that has been defined in this space, like in addition to the regression that I'm presenting today. There are studies about the Fréchet mean of graphs in this graph space. There is extension of principal component analysis, and there are also methods for uncertainty quantification. So there are many researchers works in the same setting and define different tools. But today I chose the regression because I think it's, I don't know, I think I like this model more than others. So. Okay, so we have this discrete quotient space. What we would like to do is to define a regression model. So what does it mean? It means that I have S1, X1, Sk, Xk, where S are my regressors and X are my equivalence classes of graphs, and these are my output. So I have a regressor that lives in Rp, and the X lives in my quotient space, and I would like to find a function f that goes from Rp to X over T. So this is what is called the graph-valued regression. So I want to predict an equivalence classes of graph given a regressor. So as all the methods, what I would like to do is to be able to minimize the error, the prediction error. So given my quotient metric, I want to find an f that minimizes the prediction error. This is reasonable. So the thing is that I know how to compute a regression between adjacency matrices because I'm in an Euclidean space. What I would like to do is to be able to extend the regression between adjacency metrics to a regression model between equivalence classes of adjacency matrices. So the first question is, how can I define a regression in this quotient space. And the second point is, can I use the regularity and the property of the space of adjacency matrix to fit my model? These are the two questions to answer. So, first, I define what is called a generalized geodesic regression model. So I have an f beta that goes from RP to my quotient space. And this is an intuitive way to define it. I want f beta to be a generalized geodesic, so a canonic projection of what? Of h beta. And h beta is a regression model in my total space. So h beta has this form, so it's a linear combination of my regressors with a set of coefficient beta. Yes, okay. So this is an intuitive way of defining this family F of generalized geodesics in XT as being all the F beta that are of the projection of H beta of this form. Okay? So what I'm doing is selecting all the geodesics, all the regression model here, and define this class of generalized geodesics as the canonical projection of those geodesics, of those regression models. So this is a way we can define a family of generalized geodesic regression. Sorry?
What is the sum?
This is like, I have SM that are coefficients in RP, and beta are matrix coefficients.
And what is the sum? What is plus?
Ah, yeah, that's a good point. It's just, so if S beta are scalar, which are my cases, it's just the product, the component-wise product of the scalar to the matrix. Because I'm mostly working with scalar coefficients.
And what is the sum?
It's a matrix sum.
Okay,
Component.
Yes,
Yes, sorry.
but if you sum up two ones in adjacency matrix, what do you do?
If the adjacency matrix sum up to 1.
No, what? So if you sum up element-wise adjacency matrix.
Yeah.
Adjacency matrix have 0 and 1s.
No, they are weighted adjacency matrix because I live in R n times n. Because I can have weights on nodes and edges. So I mean, I can end up in that case, but very rarely. Do you have other questions? Okay. So I've solved this question. So how can I define this family of generalized geodesics? Now what I want to do is to find a way to estimate my regression model here, which corresponds to finding optimal candidates to use, so a candidate of adjacency matrix to use to fit my model. Here again, so the question is which is the candidate T transpose X Ti in the equivalence classes of my observed X that I want to use to fit H beta. The idea here is to use the candidate that is optimally aligned with respect to the current prediction. So I have these equivalence classes, and I will pick the candidate that is closer to what? To the current estimation, of H beta evaluated in SI. So it's basically aligning the equivalence class with respect to the prediction along the line. Okay. So this is what we call the optimal regression alignment. And I mean, to read it through again, so I have this SI, XI, I have this F beta, I have a representative H beta, and I will pick the graph representative that is in optimal regression position with respect to the regression line. So this means that the distance in the quotient space corresponds to the distance in the total space between the candidates and the corresponding H beta. Okay? So this is a way to pick a candidate for the current estimation of my regression model. So just to summarize, I have an Euclidean regression defined in this space of weighted adjacency matrices, and I know how to fit this model because it's just a standard Euclidean model. I have a definition of generalized geodesic regressions through the usage of generalized geodesics in my discrete quotient space, and I define this optimal regression alignment. So the idea is to iteratively pick candidates fit a regression model, and estimate the generalized geodesic regression. So that's how we worked out the model. So this is a way to estimate a regression for set of graphs up to 2-node permutation. If we want to go back to the explanatory example, this is, as I said, regression in action. So in this case, we have this player passing network. And I'm studying FIFA 2018, so I have a championship. For each team, I can compute the player passing network. These are data available, like publicly available through StatsBomb. I have 128 player passing networks, and I want to, for example, study how the player passing networks change when I score a certain number of goals. So what you can see is when you go from 0 goal to 6 goal, you have a clear network structure that come out basically. So you have a much more clear strategy in play compared to the performance of the team when you score 0 goal. Okay, so this is just a toy example to show how you can actually use this model. And the interesting thing is that I'm using I'm evaluating this across my team. Yeah.
I have another question. So in your problem here, the SI is the number of goals scored by the team.
By the team.
But how many? Like, you don't take into account the number of goals that they receive.
Exactly. So another way could be to work on the difference, for example. So how much I'm losing or winning, because you have one player passing network per each match. So you're right that I mean, what you can suppose is that doing a 6, if you score 6 goals, probably you're winning. So it's very rare that you have 5 by the other team. But I agree, another parameter could be to work with the difference of goals.
Can I ask you, just like for this application, maybe it's just a problem, but in your case, so you're looking at different teams, but they are not independent because you don't play on your own, you play against another team.
Yeah.
And so how do you take that
account? Yeah, we don't, but yeah, that's another thing that could be done. Another question that I'm anticipating, because this always come up in this, is why are you considering purely unlabeled network? So in this case, every player has a role. So another way to handle this problem is to constrain the permutation action to a subgroup in which you allow the permutation only with players that plays in the same position. So that's another way to go. But we're not considering this. But mathematically it's the same. You can work with subgroups, for example. I mean, this is a question that always comes up. So, I mean, it's a toy example to show that you can use this model for predicting a graph from a vector or a scalar.
Sorry, I have a little question.
Yeah.
At least in the 0 goal, there are 12 nodes.
Yeah.
That represent.
So you can have different number of players. So they are considering all the players that play in that match.
So both teams.
Per each team, you might have someone.
Someone come out.
Yeah.
Okay.
Exactly. So, and this is an important point because this framework also works for graph with different number of nodes. And you encode this difference by using what we call the fictional nodes. So you add a 0 node, a node that is not connected, to graphs that has a lower number of nodes. Mm-hmm. It's a common choice that can be debatable.
Sorry, so for the number of goals, does it only consider within the regular time of 90 minutes, or also including like both the overtime of 30 minutes and possibly the penalty after the overtime? Yeah,
that's a good question. I think it's just the overall, like, despite how much they play, for how long they play.
I appreciate. I think in general this is quite promising in analyzing this relation between the passing relation between players. But I just wonder, like, intuitively, I personally think that say on one hand, if you have a better strategy to pass within different players on a team, then you may square more goals within a limited time of regular times in 90 minutes. But on the other hand, if you have a rather worse passing strategy, then you have to defer your win until, say, the overtime or the penalty trip. Yeah. There's kind of balancing how to understand if more goal really means something.
Yeah, I think there are a lot of these results can be improved for sure, because I think there are a lot of, there are a lot of questions that can be answered. Also studying, for example, the same team across different matches, or studying the difference between the number of goals, or as you said, like trying to split to understand the performance throughout the match. So it's a very rich data set. So yeah, especially if you're passionate about football.
One quick question. What happens to the fictional node with a loss in your D?
Yeah.
Is it a fixed cost to basically disappear this player, or?
It's a good question. So basically, the fictional node are added at the very first step. So here, so we decided the dimension. So we said we are picking the higher number of nodes in your data set. And we say, okay, we work in Rn times n, and we grow all the matrices to have the same dimension by adding fictional nodes. This is a common choice that creates a huge amount of problems in terms of the geometry of the space, because it's if we would have not have 0 nodes, you might end up with a manifold. Because one of the reasons why the equivalence classes has different dimension is because you can permute block of zeros without doing anything, so the action is not free. So this is so to answer your question, no, we just do this at the first step, and then we use the loss function despite you are comparing non-nodes or no.
What do you put in the adjacency matrix for the fictional nodes?
0.
Zeros or ones?
Zeros.
Okay, so you introduce some kind of bias here.
Yes, they are block of zeros. In this problem is not a big issue, because actually the nodes, apart from some that has 12 players, but is not a big problem.
Yeah.
But in other applications, it is.
Here it's nice, because if it's someone who entered at the end of the match, he didn't do a lot of pass, so of course it's going to be close to 0.
Mm-hmm. I think also this is an approximation that works better in some cases than in others, as you said. Like if you are measuring an intensity of a relation, that having a 0 makes sense. If you are measuring, for example, a transport network, having a 0 is a huge bias, because it's like comparing a road that exists with a road that doesn't exist. So it really depends on the type of applications. Yeah. So I'm gonna move now to these other type of graphs. So I don't know if you have other questions on unlabeled graphs, on abstract unlabeled graphs. Maybe come on. Okay. So just to summarize, so this is a framework that goes beyond, of course, this explanatory example. So it's a framework that allows you to work with abstract graphs that are unlabeled. We are working with this discrete quotient space, which is a natural embedding for this type of graphs, but has a complex geometry. So you gain in interpretability because you have a discrete equivalence classes of graphs, but you are working with not in a manifold setting, and you have a discrete quotient space that is a stratified space. So you have some issue in you need to work out a bit the geometry to extend some tools. And I described the regression model that we defined in this context. The work I presented can be found in these 2 papers that I did together during my PhD, actually, with Osa Verhagen and Simone Vantini. So this is about the regression model, and this is about the graph space geometries. And we are extending here principal component analysis. So the references are these 2. So let's move to this other type of object, and this is a work in progress. So I started to work on this graph type of graph recently, and I think they are very, very interesting, and they raise a lot of different questions. So here the explanatory example is histopathological images. So I have a data set of 10 patients. Oh, I'm sorry, this I didn't notice. So I have 10 patients. These 10 patients went through heart transplant or died, and they suffered from cardiac fibrosis. Cardiac fibrosis is the development of a tissue within the heart muscle that makes the heart muscle not functioning properly. So it doesn't, it decreases the elasticity of the heart muscle. So what we have are left ventricles that are cutted, and the results are these objects that are called slices. So we have slices of cardiac, of a heart, basically. And the cardiologists were interested in studying how does the fibrosis looks like. So these data are hard to acquire, as you can imagine, and they want to understand how the fibrotic tissue looks like. So they were interested in studying what they called clusters, so basically isolated patches of fibrotic tissue, and understand the difference between patients, for example, or in general the distribution of these objects. Okay? So what you see in red is a fibrotic tissue, what you see in orange is the muscle, that is then pre-processed, and we extracted a set of these objects and studied these separately as a set of what we are going to call spatial graphs. So once we have isolated the fibrotic tissue in all the patients and all the slices, we can go through what is called a skeletonization procedure. That is a standard procedure in which you extract the central line of these objects, and you can turn them into what we are going to call a spatial graph. Okay? What we need to do is to define a spatial graph and find a way to describe this set of spatial graphs. So the idea is to use this triple that is made of X that represents the set of nodes.
Can I ask a question?
Yes.
So what does a node represent?
A node doesn't really have a meaning. It's basically represent the end point of this midline that you obtain through the preprocessing. So the reason why we decided to study them as graphs is because they have plenty of holes. So it's not easy to use standard shape analysis method. So they said, why don't we look at them as a skeleton? And also because usually they are quite thick. They are quite thin, these edges. So they thought, why not looking at them as graphs? Another point about the preprocessing that I forgot is that we are working 2D, which is a big, yeah, it's not the best choice, but it's what we have. So we have these slices, so we are working with 2D pictures. Okay, so we have this skeleton, and we need to basically define the data object. So we're gonna put coordinates in R2 on the nodes, which is this space A, that I'm gonna call A. We have to encode the structure, so the connectivity, and this is represented through X, that is the discrete set of nodes, and dx. So dx is actually a metric, and in this case is what we call the shortest path distance. So it's the distance between the nodes. I forgot to mention here that we are also encoding weights in the edges that are indirectly encoded in the X. And there are different types of weights that you can put on this spatial graph. We decided to go for the percentage of area underlying the edge, that is under the edge. There are many ways you can, many different weights you can define on your edges. The idea here is that we want to be able to encode how big it was the edge under this, the shape under this edge. Okay. So by having weights on the edges, they actually become, you have a different evaluation of what is called the shortest path distance, because the shortest path distance also accounts for the edge weights. So basically, dx is representing the structure. A represents the node position in R2, and you also put a measure mu on your nodes, because this is going to be useful when we use a certain metric to compare the graphs. So this is not new. Is from a reference that I put after, and it's just a way to encode this spatial structure object. Now, so we have this set of graphs that are spatial graphs. So they have spatial position in R2. And we want to be able to compare this set of graphs that clearly has a different number of nodes and different connectivity properties. So using permutation action in this context doesn't make any sense because it's disrupting completely the spatial structure of the objects. And it's also not straightforward to use standard shape analysis techniques because you have all these holes and you want to encode this actual connectivity structure. So there is a need to define a framework for comparing these objects. So the idea was to use this distance that is gonna that was defined by Tito Avaye and co-authors, and tomorrow's talk I think it might be also about that. So I'm just borrowing concepts here. So you have two graphs that are defined as this triplet that I described before, and the idea is to use what is called the Fused-Gromov-Assessed distance. So the idea is to find an optimal coupling between the measure mu and nu, sorry for this typo, that are on the set of nodes of the two graphs. And this optimization procedure accounts for two components. The first is the distance, spatial distance between the nodes, and the second is a distance between the connectivity. So the first part accounts for the spatial positioning of the node, the second part accounts for the structure of your graph. So as I said, there is a spatial comparison, a structural comparison, and a node matching that is done by optimizing over this tie, which is a joint distribution over the two sets. So, I mean, what does it mean? It means that for compare these two objects, I want to find an optimal match between, in this case I have two nodes, in this case I have many. I want to distribute the mass of these nodes to here and the mass of these nodes to this set, and I want to account for both the distance in space and the structural distance between the connecting edges. So for example, in these specific cases, the optimal match is matching this set of these nodes with this group of nodes and these nodes with this group of nodes. These are extreme example of cases, just to show you what this distance is actually doing. One point, like if we look at the distance like this, it might seem like we are using actually this spatial distance, but this is not the case because each one of these is an isolated cluster. So they are positioned in R2 with a certain origin of the image. So we are actually comparing them as overlapped. So, okay. So it's not an actual spatial distance within the slice structure, within the 2D slice. Okay, now, the problem with this metric is that it's not invariant under rotation. So I would like to compare these graphs up to their rotation in R2. And this is motivated by this example. There might be other cases that are not strictly related to cardiac fibrosis in which you want to leverage out rotation. The reason is that, for this specific example, is that the cardiac tissue develops following the heart fiber, the muscle fiber in the heart. So you have a clear rotational, you have a clear anisotropy. So you have a clear positioning of the structure that follows this rotation, the rotation of the fiber within the slices. So the idea is to pre-align your objects with respect to their principal axis of variation. So you want to compare this object after you have rotated them with respect to their principal axis. It's one choice, there might be smarter one, but what we do is a pre-alignment basically. So we align everything with respect to their principal axis. So you can define the same metric by accounting for, by pre-aligning the data using the rotational metrics that here I'm calling OA and OB, and these rotational metrics are defined for the graphs. So it's the same exact same metric where I have pre-rotated my spatial coordinates. Okay. So this is specific to this example, but this problem is present when you work with this type. Okay, so let's go through the characterization of this space. So you have original data object you have pre-aligned your data object, and you end up in the spatial graph space, which is a metric space. So I have a metric. And it is an orbifold in the sense that you create equivalence classes of graphs, but defining the actual group action is not very easy. So let's say that you have this is a quotient set, let's say like this. So what you can do is start defining statistical methodology based on the metric only, which is not a lot, but it's something. So today I'm presenting like some preliminary results on testing, for example, because the cardiologist had as a first question, they were interested in comparing the patients. So try to understand if there were differences between the patients because they have knowledge on the type of pathology the patients had. So they wanted to understand if they were able to see that through by looking at this set of cardiac fibrotic tissue. So we would like to test to do the following test. So we want to compare distribution of the spatial graphs. So you can do this in many different ways, but unfortunately this metric doesn't really have a lot of properties. So the easiest thing to do is to use this type of test statistics, where you are just basically comparing the groups. So you have two groups, for example, one contains n1 points and the other contains n2 points. So you are comparing the distance of the data across the groups and within the groups. And this allows you to run a test for the K patients using a permutational testing procedure. There are fancier things that can be built, but it's not very easy to prove properties of this metric. So if we compare, for example, the patients, you can see that there are some patients that are different and some patients that are similar. And the ones that are similar are actually the one that shares the same type of pathology. So that was a good result. But I think the nice thing is that when you look at patients, for example, P2 and P3, so you have P2 and P3. So you are here. This is a scale from 0 to 1. And you look at the difference between these patients across all their slices. This is preserved apart from some slices that behaves a bit differently. The idea is that when two patients are different, they are different across all their slices, and is the same for P2 and P8. And when they are similar across all their slices. So you can see a difference in the distribution if you consider the patients together or if you compare them slice by slice, which is a nice result, I think. Okay, so just to summarize, this second part focused on how to work with a set of graphs that are again unlabeled in the sense that the label of the nodes doesn't make any sense, or it's not very valuable. That comes out of the preprocessing procedure, and you want to be able to compare this structure using again a concept of matching that cannot be the one that I presented for abstract graph. We define the spatial graph objects, and we use this fused Gromov-Wasserstein metric using this pre-alignment because we have a certain type of phenomenon that requires this, that suggests this pre-alignment, and then I describe a testing procedure, which is well known. So the work presented here is, you can find a lot of the content that I presented today in this paper by Tito and co-authors. And we are working on this paper about this specific application of cardiac fibrotic tissue, where we are going to describe in more detail this specific application and the theory we've developed for that. So let's conclude. So when we work with graphs, you might end up working with graphs that are unlabeled. And there are different types of unlabeled graphs that all require the type of matching that is specific for this data type. So what I presented today are two types of graphs that requires a matching. One are so-called abstract unlabeled graphs, where that can be described in a discrete quotient space that has certain properties that allow you to do statistical modeling in a certain way. And I presented regression as an example of the way you can work in this setting. The second data type are spatial graphs. That can be described using this fused Gromov-Wasserstein distance, and you can do different data analysis based on the metric, for example, testing. So to conclude, I would like to say that I think there is a need of developing tools for the last data type that I presented. These data type are there are images, like especially medical applications. There are more and more data types that looks like spatial graph or tubular structure in general. And I think there is a gap in the literature for developing methods that work for this specific data. One example is the data set I just presented, this cardiac fibrotic tissue data set. Another example are, for example, this is a project that just started in collaboration with DTU and Roskilde University. And in this case, we are working with pancreas data. So we have, again, made images. And these images encodes the vascular, the neural, and the tubular network, which are three types of networks that are that exist in the pancreas, and we need to define tools or to think about how we can work with this data structure and how we can compare subjects when they have this data structure that of course share some properties, but they are different in nature like any other data. And there are different ways to work with this data. One is to work with spatial graphs. Other is to work with, for example, topological data analysis tool that summarize the information. Or you can also work, we are also working a little bit with Gaussian random fields, for example. So you can work with, we can work in different directions, but there is a lot of things that can be done for this data type because they are starting to be everywhere. So this is the first graph ever, and thank you.
Thank you very much, Anna. Perfectly.
Time for lunch, yeah.
Yeah. We will not be late for lunch, but there is time for questions first. Please.
Thank you for the very nice talk. Can you say a word about the optimization algorithm that you use for the graph from regression?
Yes, I use the, I mean, I think you can ask, but I use the Python package, and for this optimization algorithm is the discrete case described in the Titoian's paper. So it's conditional gradient, I think, and converges to a local minima action. But I'm not really an expert there, so I'm taking the tools out of the box, let's say.
And in terms of scaling in very large graph,
I mean, this, luckily, this cardiac tissue, when you work in 2D, they're small. But yeah, so I'm working only on this specific data set for now. But for sure, when we're gonna, when we work here, it's gonna be an issue. So we need to find some solution because here you have huge graphs. So you have 3D images of pancreas structure. So one thing we are doing, we are working with a colleague on dimensionality reduction for these objects. So how can you do a dimensionality reduction that keeps the majority of the information of these spatial graphs, topological information, and allows you to use these tools that are available in the literature without getting crazy about the computational cost. I don't know if I answered that.
A quick question about the application. You have this fusion parameter, this alpha, that you can choose pretty much,
Yeah.
right? So, and sometimes the spatial information can be enough, or the other one. Did you run some analysis seeing that?
So yeah, so we are equally weighting the. We are very politically correct, so we are weighting equally the two. But I think what I would like to do is to do a bit of testing on the testing results by changing this alpha. This is in my to-do list, let's say, to see how it changes, like the results on the testing. But for now, alpha is 0.5.
Could you please come back to the slide where you define the test statistic, capital T?
Yeah.
Somehow my intuition was that you would be squaring the distances, but you don't.
This distance is, so the parameters we are choosing now, let me see. So it's squared, this part is squared.
All right, yes.
You can also put a coefficient that is, I think, is called Q in the paper, but we decided to keep Q in one. Other questions? My friend.
quick one. When you do the test, you sum basically all the pairwise distances across groups.
Within group
Why
selection.
didn't you use optimal transport between using the ground cost as the fuel because you asked?
So can you repeat? Good idea maybe, but can you repeat?
No, I mean, this is basically an MMD because you do all the...
Yeah. No, I see what you mean, yeah.
You could also find the best alignment between all the...
Yeah, that's also another way you can test. Yeah, that's a good idea. Could be. No. Yeah.
Yes, coming back to MMD, did you try to use graph kernels and to do the MMD with graph kernels because you've got it would be a simple way to do it.
Yeah, I mean the behind the scenes story is that we started using distance profile for testing, but we are not able to get a decent proof of certain hypotheses that allows us to use distance profiles. So we are now exploring other solutions until we are able to actually give it a decent proof of the fact that this metric has certain properties, basically. But yeah, I mean, we are starting exploring other solutions, but yeah, so that could be another one. I mean, with the metric, there are different things that you can do. So.
There's a question here.
I wanted to ask, you mentioned the topological data analysis in the end. How come you use, I mean, what's the advantage of using spatial graphs as you define them instead of, for example, Vietoris-Rips complex and persistent topology?
So that's a very good question. So one thing you can do is to extract some indicators from your graphs through, for example, TDA or building a persistent diagrams and then compare persistent diagrams. That could be also a solution. The thing about using the graph directly is that the original idea was to generate, so one of the original questions that they had was to be able to generate realistic cardiac fibrotic tissues to include them in a simulation. So that was one of the original questions they had, like how can I simulate, do a fluidodynamic simulation within the heart, including realistic tissues. So we wanted to start modeling the problem by working directly on the image and the data object rather than building some summary statistics and working there. So I think, yeah, that was the original motivation why we used the spatial graph. But I mean, it could be also, we can have also a lot of results, especially testing by just using, by using a TDA, for example.
Because I know that, for example, in one of these pipelines, Vietoris-Rips and some other complex that are used, you don't care about rotations, no? Which
Yeah.
But I guess you lose the distance information. Or
No, that's definitely another way to go. The reason why we started looking in this direction was that we wanted to have an embedding where every point is a valid spatial graph. So that's why we started looking at this specific embedding rather than extracting meaningful indicators from the data object.
Okay.
But yeah, I mean, testing can be done.
Thanks for a great talk. Actually, I have a question of two parts for the pre-processing of the data. It seems that first you kind of extract from the actual scan of the tissue and extract that into several patterns and treat the patterns as raw data, right?
Yeah.
And then also after the extraction of different patterns, and you kind of assign the endpoints as the nodes and the connection as the edges.
Yeah.
So for the two stages, are that kind of due to biomedical or say the doctor's knowledge, especially the first stage?
Yeah.
And then for the second stage, what is your, in general, the rough criterion to select which is a node, which is edge? Because for example, say if you have a rough region connecting two endpoints, but I can see that all the ending points, whenever you have a wedges or something, can be treated as a endpoint and then a node. So what is the general criteria to say which is node, which is not?
Okay, so first question, yes, is motivated by by what I just said. So what they wanted to do is to include in a fibrotic. So what they want to do is to simulate a slice where they encode realistic what they call the fibrotic clusters. So the reason why we isolated all the cardiac tissue is because they wanted to actually have a decent way to simulate this cluster individually. So that's the reason why we are working with this specific data object rather than something else. About the pre-processing, yeah, yours is a very good point. So what you're saying, if I'm understanding correctly, is why you're using these red nodes rather than others that you can sample from this blue, right? This is like the simplest graph you can obtain that still summarize your underlying structure. But you can put more edges like this. You can use this graph, and this will represent the same data structure. You will just have too many nodes that are not really relevant. But for example, if you look at this example, this is maybe an oversimplification, as you can see. So you might need to keep an extra node in between in order to preserve this curved shape. So yeah, it's a matter of balancing computational cost and summary of your data.
Yes, because later...
This is your question, right?
Exactly.
Yeah.
Because later, when you try to define the so-called distance between different graphs, where you have to use the proportion of their area over the whole pattern.
Yeah.
And then in that sense, the area between any two nodes actually already depend on how we pre-process the nodes, how we define the sample. So I just casually think that if we have a systematic way to define what is single and what is representative as how you did in the first part of the talk, this seems more theoretically interesting.
Yeah. But I mean, the representation is queried because you will have smaller percentage if you use all these nodes. Yes. So in this sense, you will obtain the same information, just split it in a more number of nodes. Yeah. But yeah, I mean, a lot of things can be improved.
Thank you.
Quick one, related to the last question. How do we even compare the slices if it's like two different patients? These are the images of slices, right?
Yeah.
So which two slices? Because the shapes of the hearts would be different.
Yes. So what you're saying is, can you do a level type of? So we did some testing about. We did some other testing. One was a test with respect to this dimension, like how the distribution change when you're closer or further away from the boundary, and it was not significant. So there is not much difference apparently. And the second one was with respect to the vertical axis, and again, there is not much of a difference. But there might be different reasons why we are not seeing this difference. It could be that when you work at this level, you don't see it. But if you work at this level, and we are also working with this type of data, but these are completely different. When you work at this level, you see other things because you have multiple objects in this, what we call section.
Okay, time flies when you get fun. So it's time for lunch, and it's time to thank again Anna and all of you.